so many followers.
I subscribe to you.
No, you don't. I don't have any subscribers. That's why I know. We're used to Cartesian coordinates. Our entire mathematical lives, we have plotted two-dimensional coordinates as an x, then a y. Like 2, 3. We go over an x distance of 2 units. We go up a y distance of 3 units. It's all about distances from the origin on the x-axis and the y-axis. Boom, you plot 2, 3. We can do a negative distance on the x-axis, -4. -4 units on the x-axis, 2 units on the y-axis. We also have equations with y's and x's. And we found that if you found points that satisfy the equation, we could plot those points. Example of points, if I had 0, and then typically we would have an input and an output. So an input would be the x's, the output would be the y's. We plug an input of 0, we get a y of -1. Put an input of 1 in, get a y of 1. Put an input of 2 in, get a y of 3. And you could do an infinite amount of x's to get an infinite amount of their corresponding y's. And what we found is that when we plotted all of those points, well, all of those points plotted would end up kind of melding together, and they would form a line. What is a line? It's just a collection of infinite points that satisfy a particular equation. And we know that not always is graphs of y equals x equations going to be lines. They can have different shapes to them depending on what the formula or the equation is like, okay? But it's just an infinite set of solutions, x's and y's. You're used to that. You did that your entire mathematical lives, starting in middle school. Well, let's change it up. We can list coordinates instead of as an x and a y as an r and a theta. They're called polar coordinates. Okay? Now, it's important to understand if we had the x's, y's, x was an x distance, y was a y distance from the origin. Okay, x distance, y distance. R theta, r is just your overall distance from the origin. It's not an x distance, it's not a y distance, it's just your overall distance from the origin. Theta is the angle at which you are taking that distance. So we're not really caring so much about x units and y units on the x-axis and y-axis. We're thinking about angles and distances from the origin. Now, once we start thinking about angles, we need to switch our brains into, kind of the unit circle world, where we had a x and y axis, but we said, oh, the x-axis over here to the right, this is an angle of 0. This up top here is an angle of pi over 2. This is an angle of pi. It's just a distance around a circle, a unit circle. This would be an angle of 3 pi over 2. Okay, so this would be the thetas. Now, the way to think about r's is to think about circles with different radiuses. Because a circle with radius 1, every single point on that circle has a distance from the origin of 1. Circle of radius 2. Every single point on a circle of radius 2 would have a distance from the origin of 2. So I can kind of draw circles to help me understand distances. This is a radius 1. Let's say this is a radius of 2. And this is a radius of 3. I just had to wiggle my mouse. All right, so if I were to plot, and you can, put this as a distance of 1, distance of 2, distance of 3. If I were to plot the point 1 pi over 2, Now, unlike x's and y's, with inputs and outputs, x being the input, y being the output, I actually like to think of these things as thetas first, then r second. So it's almost like we do the second thing first, and then we do the first thing. I was wondering yesterday, why isn't it theta first, then r? Because mostly people think about the angle first, then the distance. It's not theta, then r, because we list coordinates in alphabetical order. Is Skinner here? Skinner's not here. There he is. Okay. Not in his regular seat. That will be on YouTube forever. Okay. So the reason why it's r then theta is because we list them in alphabetical order. R comes before t, so r then theta. Well, here's what I would do to plot the point 1 pi over 2. I would start with kind of like my angle. I'm going to use this line to help me demonstrate what I'm kind of thinking in my head. I start with the line or the angle at 0, and I take the angle up to pi over 2. Then I say, okay, I need to be a distance of 1 from the origin at that angle of pi over 2. Boom, I've plotted the point 1 pi over 2 using polar coordinates. That is much, much different from the Cartesian location of 1 pi over 2, which would be like right there. Okay? It's different. We have to switch our brains because it's different. Now let's look at 3 5 pi over 6. Well, we have to understand where the angle 5 pi over 6 is. It's 1 pi over 6 less than 6 pi over 6. That is over here. Okay, here's the angle 5 pi over 6. I will go a distance of 3 units away. 1, 2, 3. Here is the location of the polar coordinates of 3 5 pi over 6. Now, we could have negative r's and we could have negative theta. Example is like negative 2 pi over 3. Again, what I like to do is go to my angle first of pi over 3. Here's pi over 3. And think about a distance of negative 2. Well, that means instead of going out to pi over 3, we'd kind of go away from it and kind of extend this in the negative direction, and all of a sudden I'm at negative 2 pi over 3 over here. So it's kind of like taking that line and just going away from it. I could have negative angles and negative radiuses. Let's look at negative pi for my angle and negative 1 for my radius. I would go to the right away from the angle to get to negative 1, negative pi. Now, the great thing about polar coordinates, well, it's just one interesting thing about polar coordinates, is that unlike Cartesian coordinates, there are multiple points that can plot the same point on the plane. Who could give me an example of another point that could plot the same point as 1 pi over 2? Ms. Cusay? Perfect. If I went all the way to 3 pi over 2 and just went in the opposite direction, boom, I would have this same point. Could somebody give me another one for 1 pi over 2? 1 negative 3 pi over 2. If I went in the negative direction for my angle and had a positive radius, that works as well. Give me another one. Mr. Noakes? We could go around the entire circle to 2 pi and add another pi over 2. That's the angle 5 pi over 2, and that would have also a radius of 1. So it turns out there's an infinite amount of ways that we can list off these points on the coordinate plane. Okay? So that's something we can take a note of. Question? Yep, you could do -1, -5, or 2.
How do negative radius work? You just go to the opposite side.
Yes, the opposite side of the angle. You go to your angle, and instead of going out towards the angle, you go the other way. Okay, very important to understand that. So note, if I have an r, then a theta, that's going to be the same as if I have the same r and add a multiple of pi, a multiple of 2 pi plus my theta. So it's just like keep the same radius and go around your circle again, either in the negative direction or the positive direction. We had the negative 3 pi over 2. That was going around in the negative direction. Okay? Or that's the same as having my opposite r and going around half of the circle. So a multiple of pi. Okay? So we can do negative angles, positive angles. We can do positive radiuses and negative radiuses. Now, we already graphed a Cartesian y equals 2x minus 1, where we took x's, like x equals 0, x equals 1, x equals 2, and we found y's. We can graph polar equations as well. Equations for polars are typically r equals some function of theta. Okay, so either you can say r of theta is equal to that, or you say r is equal to that. Okay, so in this situation, for all of our polar graphs, theta is typically my input, and then r is my output. Mostly because it's easy to plug in thetas and get r's. It'll be hard to start with r's and plug in thetas. It could go either way, but typically it's r as my input, theta as my output. Okay? Now, how are we going to graph these? Well, just like we would for a Cartesian, we'll just pick a bunch of thetas, find their corresponding r's, and then plot those points. All right, here we go. I'm going to pick a bunch of thetas. Start with 0. I'll do pretty much all of the interesting easy triangles to work out. Pi over 6, pi over 4, pi over 3, and I'll stop at pi. Pi over 2, I'll go to 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Whoops. Okay, so how am I going to find the r's? Well, we just plug in the thetas. Cosine of 0 is 1 times 3. That gives me the point. Now, theta comes second, so it would be 3 as my r, 0 for my theta. Ends up being at the same location as the point 3, 0 on the Cartesian plane. And that should make sense. Anything with the theta of 0 is the same as the Cartesian point. But that's the only one where it works. Everything else you got to think about angles and distances. Let's try pi over 6. It'd be 3 cosine 2 pi over 6 was pi over 3. Cosine of pi over 3 is a half times 3 is, let's change this to 4. Why am I doing this to myself? This will be easier to work with. 4, 4, this is 4, this is 4. Okay, so you got the point 40. Cosine of pi over 3 is a half. 4 times a half is 2. So I get the point 2 comma pi over 6. Pi over 6 is my angle. The radius is 2. Start with your angle. There's my angle of 0. Go to the angle of pi over 6. Pi over 6. Tick off 2 units of distance there. Either think about a circle of radius 2, or you can kind of just eyeball it. Question? So theta that I chose is pi over 6. The thing with what I'm doing with theta is I'm multiplying it by 2. So I end up with the angle of pi over 3 in here, but my input being multiplied by 2 is pi over 6. Cool? So let's do a couple more, and then we'll just quickly go through the other ones. So 4 cosine pi over 4 times 2 is 2 pi over 4. That's pi over 2. The cosine of pi over 2 is 0. So that gives me pi over 4 and 0. R comes first, theta comes second. So watch. I go up to the angle of pi over 4, which is right here, and then my radius is 0. So it looks like we're at the point 0, 0, but actually this point right here is the point 0 pi over 4. Okay, and we kind of see the beginnings of my polar graph. I have that. Close. Okay, let's keep going. I can have pi over 3, r times 4 cosine of 2 pi over 3. Cosine of 2 pi over 3 is negative a half. All of a sudden, I get negative 2 pi over 3. Okay, this is my negative radius. Let's see what happens. I go to the angle of pi over 3, but then I'm going to have a radius of negative 2. Think about going a distance the opposite direction of negative 2. If I did pi over 2, it'd be the cosine of pi. I'd have negative 4 pi over 2. So down here. And we can continue my graph. If I did 2 pi over 3, I'd have also a distance of negative 2. So I would go to 2 pi over 3, which is my angle here. My distance is negative 2, so I'd go down here. I'd have this point right here. Okay, so all of a sudden, I started curving. This is bad. So I started here, came this way, I went this way, and then I'm coming back this way. Now I did 5 pi over 6. 3 pi over 4 is next. I kind of got out of. If I do 3 pi over 4, let's see what I'd have. So I plug in 3 pi over 4. It end up with 6 pi over 4, which is 3 pi over 2. The cosine of 3 pi over 2 is 0. I'd have a radius of 0 and then 3 pi over 4. All of a sudden, I have another point at what we are used to thinking of as 0, 0, but also is 0, 3 pi over 4, and 0 pi over 4. So my graph actually goes back to where it's already been on the coordinate plane. Let's do a couple more. back to 5 pi over 6. That's still in the second quadrant. If I plugged in 5 pi over 6, it'd be 10 pi over 6. It would be the cosine of 5 pi over 3, which is positive a half. Positive a half times 4 would give me a positive 2. And then let's stop at pi. The cosine of 4 pi, the cosine of 2 pi is all I'm doing. The cosine of 2 pi is positive 1 times 4, give me the point positive 4 pi. So I finish off with those 2 points. I go to the point 5 pi over 6, my angle, and then 2, that's right here, and then pi and 4. Here's pi and my radius of 4. All of a sudden I have this. Where do you think the next point would be located? Yeah, right here. This would be the point. The angle would be 7 pi over 6. And I'd have a radius of positive 2. So 7 pi over 6, 1 pi over 6 after 6 pi over 6, 2. Then I would go to the pi over 4. That would be 5 pi over 4, 0. Then after 5 pi over 4 comes 4 pi over 3. Well, if I plugged in 4 pi over 3 into my formula, I would get a radius of negative 2. After 4 pi over 3, I'd have 3 pi over 2. 3 pi over 2 plugged in would end up giving me a radius of negative 4. Then I'd have, 5 pi over 3. 5 pi over 3 would give me a radius of negative 2. And all of a sudden, I'd have 5 pi over, this would be 7 pi over 4. That'd give me a radius of 0. Keep going. I have 2 more points. I have 11 pi over 6. That'd give me a radius of positive 2. And I'd have 12 pi over 6, or 2 pi. That'd give me a radius of 4. And then I would continue to go around the circle. But when I continue to go around the circle, we would just go along the same path of this graph over and over and over and over again. It does not go on to infinity. It does not increase in values. It does not go anywhere. This is it. Repeated as we continue to go around the circle. Okay? Pretty cool, huh? I think so. Your calculator can do this as well, but you got to tell it what to do. So go to your calculator. Your calculator is used to being set. If you go and have your calculator all reset, it is set for y equals f of x's Cartesian coordinates. Okay? If I press y equals, I see y equals. If I press this button here, I get x's, f of x's. Okay, so y equals x's. Well, if you go to mode and you go down to polar, or to function, you can slide over to polar. All of a sudden, your calculator can be taught to, instead of having y's equals x's, have r equals, and then if we press this button, notice it's xt theta. Well, boom, if I press this button now, all of a sudden I'm getting thetas and not x's anymore. Okay? So your calculator now is in polar equation mode. And you can graph any polar equation like 4 cos 2 theta. And see this lovely flower pattern. Okay, now what we find out is that the maximum distance is this 4. Well, if I change this to, say, 8 cosine 2 theta, the petals are just going to get a little bit larger, because that's the maximum distance I could have away. What we find is that this 2 theta here, this kind of helped me plot some points in between 0 and 0, or like the angle of 0 and the radius of 0. Well, if I changed it to like 3 theta or 4 theta, watch what happens. I would change the amount of petals that I would have. All of a sudden, I have 3 petals. Watch what happens if I go to 4 theta. I have 8 petals. If I go to 5, maybe I'll have 6. No, I have 5. I have the same amount. I have the same amount of petals as the odd numbers. If I go to 6, I should have a lot of petals. Okay, really cool. If I just have 1, if I just have theta, I would just have 1 petal. What would 1 petal look like? Yeah, it would just be a circle. Kind of like an oval, actually, not necessarily a circle. Okay, pretty neat, right? Well, go ahead and try to discover some other cool graphs, like simple ones like this: r equals 3, theta equals 5 or 6, r equals theta. What would r equals 3 look like? What's that simply? Yeah, circle with a radius of 3. So radius 3, circle, boom. That's r equals 3. What would theta equals pi over 6 look like? False. It would be a line. So we don't have theta here, but how do I get a circle? This is pretty much telling me whatever theta I have, r is going to equal 3. Just like how when we have the graph of y equals 3, we don't just have a dot at y equals 3. What do we have? A line through y equals 3, right? No matter what x we use, we get a y of 3. Here, no matter whatever theta is, r is 3. Here, it's almost like x is equal to a value. When you get x equals 5, it would be a vertical line. Here, this is whatever r you have, theta would equal pi over 6. Well, theta equals pi over 6 is right here. R could be positive. R could be negative. This would be theta equals pi over 6. Who could tell me without graphing what they think r equals theta looks like without graphing it? Would not be flowers, actually. A spiral is correct. Why would it be a spiral, Mr. Mayor? Cheater. That's good. Oh, yeah. Because as my angle increases, what am I starting at? 0, 0, right? My angle is 0. Well, this is my angle 0. And let's use our handy-dandy kind of angle tool to help us. When my angle is 0, my point is 0. Let's just go by the pi over 4s. When my angle is, pi over 4, my radius is pi over 4. That's almost 1. When my angle is pi over 2, my radius is pi over 2. Pi over 2 is a little bit more than 1. When my angle is, let's just go to pi. My radius is pi. What's pi? That's 3.14. Well, this is the radius of 3, so here's 3.14. If I go to 3 pi over 2, that's 3 times 3 is 9 point whatever divided by 2, so that's like 4.5, so we'll probably write here. So all of a sudden, if I go to 2 pi, 2 times pi is 6 point something, so I'm probably over here. We can see I would be spiraling out And as my angle gets bigger, my radius would get bigger and bigger and bigger. Okay, go ahead and confirm that by graphing. And go ahead and play around and see if you can have some cool graphs of polar equations that we can show the entire class for fun. This should have been in blue. You know what a cool one is? Secant. Secant is just a vertical line. You'd think it's more complicated than that, isn't it? Tangents. Let's look at tangents. Tangent fancy? That's a little fancy. That's why you have to know what you're graphing instead of having the calculator graph it for you. Yeah, just the basic ones that we're going to do today. This is tangent, tangent, tangent theta. We looked at this earlier. If you zoom in, it looks kind of wild. Okay, so very cool stuff with these polar equations. Now, for your quiz, I'd expect you to have some problems where you ask somebody to plot a couple polar coordinates, maybe 4 questions, quick questions. Then make sure you have negative angles and negative radiuses on your quiz. I'd expect you to ask somebody to graph a polar graph without the use of a calculator and for a defined range or a defined theta kind of domain. So maybe between 0 and pi, and you'd say pick 6 points. Make sure they're graphing the correct 6 points. Probably include the graph of one of these, probably an r equals or a theta equals, just so that we understand that. And you can do that, okay? Next thing we're going to learn is how we can convert polar coordinates into xy coordinates or convert xy coordinates into polar. So let's start with an xy coordinate, 2, 2 root 3, and figure out what it is in terms of r and theta. Well, guess what? This comes from an x distance and a y distance. What can we create if we know an x distance and a y distance? A triangle. And from the triangle will come equations. We will use triangles, right triangles, to help us convert. So 2 root 3 is telling you that this x distance here is 2 and this y distance here is 2 root 3. I want an r, then a theta. So that means I want r there and I want theta there. How can I find r? Pythagorean Theorem, right? A squared plus b squared is equal to c squared, or r squared is equal to x squared plus y squared, which means r is equal to the square root of 2 squared plus 2 root 3 squared. 2 squared is 4. 2 root 3 is 4 times 3, which is 12. So 4 plus 12 is 16. Root 16 is 4. How can I find the angle? Well, good old Chief SOHCAHTOA can help us with that. Remember, tangent of an angle in a right triangle is equal to the ratio of the opposite side over the adjacent side. Well, we already know what the y is and the x is. I kind of want to step ahead. If I wanted to find theta and I had a calculator, you would take the tan inverse of both sides. Keith, you're killing me. We'll have plenty of time to work on our quizzes. The 2's will cancel. You'll just have the tan inverse of root 3. You can plug that into your calculator, or you should be able to kind of figure out, by kind of shrinking this triangle, by dividing each side by 2, actually dividing each side by 4, that this would be the same as a side of root 3 over 2 and 1/2. Well, if your y is root 3 over 2, it is a longer side than the x of 1/2. Where is this angle theta? The theta would be pi over 3. All of a sudden, we have turned 2 comma 2 root 3 into the polar coordinates of 4 and pi over 3. Just using our friends' z-right triangles. Well, if I had r and theta, and I want to turn it into an x and a y, what would I do? I would continue to use my friend, Chief SOHCAHTOA. Yes? Where's your pass? One 3 pi over 4. Well, let's create our right triangle. We know theta, we would consider that reference angle to be 3 pi over 4. And r, let's change r to 2. You got to get a pass. I can't just let you go.
Like from the office?
Yeah. You have to get one of those yellow passes. This guy can be dismissed at this time because he has this. Or the office should call down and say, send this person. And I'll say yes.
Okay.
So text your mom to call the office or something like that.
Yeah.
You can't just leave class right now.
Okay.
I don't know why it's funny. Welcome to school, Lake Travis High School. Can't just leave whatever.
So can I go
No. Again, no. Maybe after the lesson's done, you can go.
Okay.
Now I'm all messed up. Where was I? Gosh.
Triangle.
Yeah, triangle. Thanks. Great. I got to find this y. I need to find this x. Okay? Well, guess what? Sine and cosine will help me. I know the sine of my angle will equal the ratio of the opposite side over the hypotenuse. I know that the cosine of my angle will equal the ratio of the adjacent side over the hypotenuse. I can find my y-coordinate just by multiplying 2 by the sine of 3 pi over 4. I can find my x-coordinate by multiplying 2 by the cosine of 3 pi over 4. Sine of 3 pi over 4 is positive root 2 over 2 times 2 is positive root 2. The cosine of 3 pi over 4 is negative root 2 over 2 times 2 is negative root 2. This should make sense The x distance is the same as the y distance because my angle is at 3 pi over 4. We know at 3 pi over 4 we're at a 45-degree angle, and these distances are the same because we have an isosceles triangle. It's just in the correct quadrant, x being negative because cosine in the second quadrant is negative. In general, if you have polars and want to convert them to Cartesian, your x-coordinate will just be r cosine of the theta. That's just solving for x every single time you multiply by the radius or the hypotenuse. Y will equal r sine of theta. This goes for any x and any y. If you have Cartesian to polar, we will be able to find r by taking the square roots of the sum of the length squared, and we'd be able to find theta using any ratio, tan, sine, cosine, but since you're already given y and x, might as well use tangent. Now the tough ones to convert would be the ones from Cartesian into polar. For example, the last one over here, root 3 negative 1. Easy to find r, square root of root 3 squared plus negative 1 squared. That's just going to be 2. But it's tough to find theta without a calculator. We know that the tangent of theta would equal the ratio of the y over the x. And we figure that out without using our calculator and using tan inverse. Well, we should be able to. Think about where the coordinate is located. Root 3 is greater than 1. Let's say it's right there. Negative 1 would be right there. So we're at this location where the x is root 3 and the y is negative 1. Well, to kind of make that a triangle that I am familiar with, I can divide both sides by 2 and kind of shrink the triangle. Still would help me find the angle. Well, when we have a further x distance than a y distance, and we have root 3 over 2 and a half, we're talking about a reference angle of 30 degrees, or a pi over 6. We are in the fourth quadrant at the pi over 6, giving us 11 pi over 6, which is 1 pi over 6 less than 12 pi over 6. So this is the same as 11 pi over 6. I'd expect you to be able to do a couple of these conversions without the use of a calculator. Okay? These are easier. Our cos theta is your x. That's messed up. It should be 4 pi over 3. Our cos theta is your x. Our sine theta is your y. Cosine of 4 pi over 3. 4 pi over 3 is in the third quadrant. The cosine is just a half times 2. It would be actually negative a half because we're in the third quadrant. Sine of 4 pi over 3, we are in the third quadrant. The sine is root 3 over 2, but it's negative. Root 3 over 2 times 2. Negative root 3 over 2 times 2 would be negative root 3. And this would be the xy. If you started with r theta, this would be the r theta if you started with xy. Okay? I'd expect you to be able to convert a couple points. I'd expect you to graph. Last couple things. What is cool about this is we don't have to just use these to convert points. We can help convert equations into Cartesian equations or to polar equations. Example, if I have y equals 2x minus 1, I can actually convert this into a polar equation because I know y is equal to r sine theta. I know x is equal to r cosine theta. I could solve for r, and I can actually graph this as a polar, and it would be the same as y equals 2x minus 1. What would I do? I would solve for r by subtracting 2r cos theta is equal to -1. Factor out the r. I get r is equal to -1 over sine theta minus 2 cos theta. Go ahead and graph that in your calculators. I bet you it looks like a straight line, just like y equals 2x minus 1. If it just shows you part of a line, go into your window and change your theta step to a smaller value. Is it a straight line? Yes. Change your theta step, which just tells you how many points to put in, to a smaller value, and things should increase and become a larger line. Go into your window, and it'll give you theta min, theta max, and theta step, which is kind of telling you how many points that they're plugging in. You change your theta step to something smaller, it will give you more points, and you will see the radius increase. And, yeah, perfect. Probably too small.
Oh, okay.
There you go. Okay. Now, if I had a polar equation, so this is the one that we graphed already with the 4 petals, I can convert it to a Cartesian graph. R is equal to the square root of x squared plus y squared, and theta is equal to the tan inverse of x over y. Just shows you that you could graph that, and I did so earlier, and that's what I got. Now, I had to square things on both sides because they didn't like the square root, but after I squared things on both sides, I got that guy, which is the exact same thing as we saw earlier, only this is expressed in terms of x and y. Now, for this situation, I would not solve for y. I cannot solve for y. It's not a function. It would have to be multiple, lots and lots of different pieces for each piece. Here's the y equals. Yeah, go ahead and do that. Solve that and get that. Right? And I think that's just, I think that's just one of them. Okay? All right, so that's it. So again, for your quiz that you are going to create, a couple of converting points into x's and y's, or converting x's, y's into r's, thetas, a couple of graphs, a couple of plotting, just like that, okay? I would have a couple easy graphs, probably one more difficult graph where you need to plot a bunch of points, give them a range and some values, and go from there. Probably one question's like express this point 2 different ways. That way you can just, add half a circle and then make the radius negative. Boom, it's the same point, et cetera, et cetera. All right, thank you. You can go to work now.